Hi class, we are on chapter 5.4, half-life of a radioisotope. So we are going to be looking at aging. We use radioisotopes to determine the age of anything. Don't want to go into specifics here. And we're going to specifically look at a half-life and what that means and how we're going to use it to calculate determining how old something is. So a half-life. So what is a half-life? The half-life, we take a sample, a radioisotope, and the half-life is how long it takes for half of that sample to decay. So let's look at this iodine as an example. So we're looking at a radioisotope, iodine 131, and consider this as 100%. And we want to know how long it takes to get to half-life. Half-life is 50%. It gets to half of its original value. And in this picture, it takes 8 days for it to get to 50% of its original value. So knowing the half-life, we can determine how many half-lives. We can use that information to figure out how much is left after a certain amount of time. So for instance, if you look at the bottom here, we start out with 20 milligrams of iodine 131. We know that one half-life is 8 days. So after 8 days, it'll be at 50% of its original value, which makes it 10 milligrams. Now, we want to do a second half-life. So we take this 10 and it's now cut in half again. That's 16 days. It's taken 16 days. That's 2 half-lives because 8 days here and another 8 days here. And now we are at 5 milligrams after 2 half-lives. But let's go to 3 half-lives. So now we have another 8 days added on, and that 10 milligrams went to 5 milligrams, and now half of that is 2.5 milligrams. So after 24 days or 3 half-lives, we are at 2.5 milligrams. That is what's still a radioisotope. The rest is gone, it's decayed away. So a decay curve, this is a curve that shows exactly the same information that I discussed right now. So if you look here, we start at 20 milligrams. This is the amount of 20 milligrams. And the half-life is 8 days. So the increments here are by 8. So 8, 16, 24, 32, 40. And it illustrates, obviously, it's going to go down because it's decaying away. So it's losing half of its original value with every half-life. So we have 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, and 5 half-lives. And it shows you the amounts for every half-lives, and it's half of what the prior one was. So radioisotopes, they have some that go for very, very long time, and then there's some that are very, very short. So here's just an idea of some of the radioisotopes. We have carbon-14, a half-life. Now remember, this is half of its original. It will take 5,730 years for that to get to a half-life, and that's a beta radiation. Potassium 40, so it has a half-life of 1.3 times 10 to the 9 years, and if I'm correct, that's 1.3 billion years, and that is a half-life. That's beta and gamma radiation, and it goes through, and you can see. So, but we also have some that are used, but those are natural occurring radioisotopes. If you look at some medical radioisotopes, you want these to be as short as possible. You don't want to keep these in the body longer than what it is. You want it to decay. So for carbon-11, the half-life is 20 minutes. Chromium-51, 28 days. This one's 8 days. This is 2 minutes for oxygen-15. So obviously for the medical ones, you want them to be very, very short. So now we're going to look at how to do a half-life calculation. So the radioisotope strontium-90 has a half-life of 38.1 years. If a sample contains 36 milligrams of strontium-90, how many milligrams will remain after 152.4 years? These calculations are not that difficult. They're just, again, something new, but believe me, you guys have done far more harder than this. So what do we have? We're given the starting quantity, which is 36 milligrams of SR90. We know that a half-life, one half-life is 38.1 years. And we want to know how much is left of this sample that we started out with 36 milligrams after 152.4 years. So we've got to figure out how to connect these to get to that answer. Okay, so we need to write a plan to connect everything. So we have years. We're going to start with years because we're going to look at either 152.4 years or the starting amount. So for now, we're going to look at years. We can go from years to a half-life. Why can we do that? Because one half-life equals 38.1 years. So that is a conversion that we can use. And then we can take those half-lives and then determine from the starting amount how many half-lives we've gone through to determine the remaining amount. So basically there's kind of two calculations that are going to take place. We need to figure out how many half-lives, and then from there we will plug in those half-lives to figure out what the remaining amount is. So here's the conversion. One half-life equals 38.1 years. And remember, we can put it in either form depending on how we need it. And we're going to look at 152.4 years first because we need to determine how many half-lives. And there's not really a fast way to plug these in. You have to do them in two separate equations because if you try to do it half-fast, you're not going to come out with these same numbers. And if you find another fancy way of math, let me know. But this is why I know I've tried to plug it in different ways to be creative, and it's never worked out. Okay, so we start with 152 years. So we're going to put 38.1 years on the bottom and one half-life on the top. So when we cancel out, this gives us 4 half-lives. So it's going to take 4 half-lives for us to determine, excuse me, it's going to take 4 half-lives to fulfill that 152.4 years. So now we have another step. So think of this as the first calculation, and here is the second calculation. So we start out with 36 milligrams, and now we just keep halving this until we get to 4 half-lives. So this is 1 half-life, so 36, and half of 36 is 18, half of 18 is 9, half of 9 is 4.5, half of 4.50, is 2.25. So now let's count this. This is 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. So the remaining amount is 2.25 milligrams of SR90 after 4 half-lives, or 152.4 years. Okay, so now let's do another problem. Now this problem involves the Dead Sea Scrolls. Carbon-14 was used to determine the age of the Dead Sea Scrolls. If the Dead Sea Scrolls were determined to be 2,000 years old, and the half-life of carbon-14 is 5,730 years, what fraction of this half-life has passed? So let's take a look at the information we have here. First of all, the Dead Sea Scrolls are determined to be 2,000 years old, but the half-life is actually a larger value. So it hasn't even the Dead Sea Scrolls are not even as old as the half-life. So it wants to know what fraction of that half-life has passed, because it's not gotten to the complete 5,730 years. So we're going to do some more math here. So we need to plan a way to get to think of a stepping stone. So we have the years, we're going to use the years, and then we're going to use the half-life, and that's going to provide us a fraction of the half-life. So what's the conversion we're going to use? We're going to use 1 half-life equals 5,730 years, and we're going to use it either way. That's going to allow us to cancel out the units. So when we set this up, we're going to set up with 2,000 years. We're going to put the 5,730 years on the bottom, 1 half-life on the top, and we're going to cancel out the years. And the fraction is 0.3 half-lives. I don't like that they left this answer like this. Remember, if you times this by 30, it's 100, it's 30%. So 30% is what has passed in this half-life based on this problem. So I really don't like that they left it 0.3 half-life, but that's what they did. But times 100, 30%. 30% of that fraction has passed. So the half-life of iodine 123 is 13 hours. How much of a 64 milligram sample of I-123 is left after 26 hours? So let's take a look at this one. So we are given a starting amount of 64 milligrams. 26 hours has elapsed, and we know that 1 half-life is 13 hours. So now we're going to go through the same process. We're going to figure out, using hours, how many half-lives have passed. So we're going to do the same thing as we did with the original problem. It's kind of in 2 steps. figure out the how many half-lives we need, and then use that to determine the amount that's left over. So 1 half-life equals 13 hours. We're going to set that up how it allows us to cancel out hours. So 26 hours divided by 13 hours, that is equal to 1 half-life, gives us 2 half-lives. So now we're going to do the second step, where we take 64 milligrams as our starting, divide it by, cut that in half, so that's 32 milligrams, and then 16 milligrams. So if we count that, that is 1 half-life. I don't know why there's an arrow here. Ignore that arrow, that shouldn't be there. So 1 half-life and 2 half-lives. So at the end of this, the answer for this question is 16 milligrams of iodine 123 is left after 26 hours.